Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Kleppner and Kolenko. We will continue to discuss topics from Chapter 7, Rigid Body Motion and Conservation of Angular Momentum. In the last class, we have talked about the vector nature of angular velocity and angular momentum. Today, let's see the relation between linear velocity vector and angular velocity vector. Consider a rigid body rotating about some axis. The direction of the axis is given by a unit vector n cap. So as the body rotates, each of its particles describes a circle around the axis of rotation as shown in this figure. So a vector r from origin to any particle, as you can see, when the particle rotates in a circle, this r vector is going to sweep out a cone. The figure shows the result of rotation through an angle delta theta about the axis along n cap, and you can see that throughout this rotation the angle phi between n cap and r vector is a constant. And the tip of the r vector is going to move in a circle. And what's the radius of the circle? So if you redraw this circle here, so you can see this angle is delta theta, and this is the r vector, this angle is phi, so this side is going to be r sine phi. Okay, so the radius of the circle is going to be r sine phi. Let r of t be the position vector at time t, and after a time delta t, the position vector changes to rt plus delta t. And the separation between these two positions is given as delta r. Okay, now what's the value of delta r? Let's take this triangle and draw it here. So you can see this angle is delta theta, half of that is delta theta by 2, and this side is nothing but radius of the circle given by r sine phi. So this is r sine phi, this is delta theta by 2, so this side is going to be r sine phi sine delta theta by 2. So this is half of the length. The other half is also going to be the same amount. So the total length delta r is going to be 2r sine phi sine delta theta by 2. Okay. Now, if delta theta is very small, you can make use of the small angle approximation where sine theta can be approximated to theta, right? So sine delta theta by 2 can be approximated to delta theta by 2. So the magnitude of delta r is going to be r sine phi delta theta. Or delta r by delta t is r sine phi delta theta by delta t. In the limit delta t tends to 0, this becomes a derivative. So modulus dr by dt equal to r sine phi d theta by dt. Now let's talk about the directions here. So in the limit delta t tends to 0, you can see that dr by dt, it is tangential to the circle, and also it's perpendicular to the plane of r and n cap. Okay. Now from the definition of cross product, we know that the cross product of two vectors is going to be perpendicular to both the vectors. And as I said, dr by dt is perpendicular to both r and n cap, which means I can represent dr by dt as a cross product of n cap and r. So I write dr by dt equal to n cap cross r d theta by dt. Let's check whether this equation is correct. First, look at the direction. So since this is a cross product, dr by dt should be perpendicular to n cap and r, which is right. And look at the magnitude. So how do you take the magnitude of a cross product? magnitude of first vector into magnitude of second vector into sine of the angle between them. N cap is a unit vector, its magnitude is 1. So this is essentially magnitude of r d theta by dt multiplied by sine of the angle between n cap and r. This angle is phi, so this is r d theta by dt sine phi, which is nothing but the magnitude of dr by dt. So in terms of magnitude and direction, this equation is perfectly fine. Now we know that the left hand side dr by dt, rate of change of position, is nothing but linear velocity v, and d theta by dt is the angular velocity omega. Multiply it with n cap, which is the direction of the axis. This gives you the angular velocity vector omega. Okay, so the vector equation is vector v equal to vector omega cross r vector. So this is the geometry. You can see the linear velocity is perpendicular to both omega and r, where omega is along the axis of rotation. And finally, coming to the conservation of angular momentum. So in the case of translational motion, we have seen that when the total force acting on a system is 0, its linear momentum, or simply momentum, is conserved or remains a constant. In other words, in the case of an isolated system, the linear momentum is always conserved. So let's consider a system of n particles with masses m1, m2 all the way to mn. Let's assume that the system is isolated, meaning the external force or torque acting on the system is 0. So we are going to talk about only the internal forces, or forces arising entirely due to the interaction between the particles. Okay. Now if I take a particular particle j, now the force on the jth particle is going to be force due to first particle plus force due to second particle all the way to force due to the nth particle, right? So I can write force on jth particle Fj equal to summation over k from 1 to n Fjk, where Fjk is force on particle j due to particle k. So k runs from 1 to n. So this gives you force due to all the particles on the jth particle. Now, one thing you have to particularly remember is that in evaluating the sum, you need to neglect the term k equal to j, because when k equal to j, the force is Fjj. This is force on jth particle due to the particle itself, which is 0, right, from Newton's third law. Okay. So if you are very strict about mathematical notation, ideally you should be writing summation over k from 1 to n, k not equal to j. That's the correct notation, but even without that, this is perfectly fine. Okay. Now the torque on the jth particle tau j is nothing but rj cross fj, where rj is the position vector with respect to some coordinate system. Now instead of fj, I can write this summation equation. So tau j equal to rj cross summation over k fjk. Now, so for simplicity, let's consider only two particles, j and l. So tau jl be the torque on particle j due to particle l. So I can write tau jl equal to rj cross fjl, where fjl is the force on j due to l. Now from Newton's third law, we know that if particle L exerts a force on J, in return J is going to exert a force on L, which is nothing but FLJ. So you will have a torque associated with FLJ. Let's call it as tau LJ. So this is the torque on particle L due to particle J. So following the same definition, I can write FLJ equal to RL cross FLJ. So the total torque acting in this system of two particles is sum of tau JL and tau LJ. Okay, so the total torque is going to be tau JL plus tau LJ, which is RL cross FLJ plus RJ cross FJL. But from Newton's third law, we know that the internal forces are equal and opposite. So Fjl is nothing but minus Flj. So the total torque tau jl plus tau lj equal to RL cross Flj. And instead of Sjl, I can write minus Flj. So this is minus Rj cross Flj. Flj is common, take it outside, so you have RL minus Rj cross Flj. So this I am going to write it as RJL. So let's draw this geometry. So I have particle J and L with masses Mj and Ml. So Rj is the position vector of J, RL is the position vector of L. So and you have forces Fj, L and Flj acting in the opposite direction. So if you complete this triangle, you will find that the third side is RJL. So RJL is nothing but RL minus RJ. Now, if you are talking about central force, now we know that in the case of central force, the force always acts along the line of separation. So which is what we have shown here, right? So in this case, the forces are acting along the same line as RJL, which is the separation vector from J to L. So in other words, FLJ is parallel to RJL, and we know that in the case of two parallel vectors, the cross product vanishes. So in the case of central force, the total torque acting between two particles J and L, tau JL plus tau LJ equal to 0. So if you consider all the n particles, the same thing you can extrapolate. So the torque always act in pairs and all the internal torque cancels. So the net torque due to the internal interaction, or the net internal torque, is going to be 0. And we know that torque tau equal to dl by dt, and tau has two components, one due to the external force and one due to internal force. Since we are considering an isolated system, the external torque is already 0, and we have shown that the internal torque is also 0. So the left hand side is 0, which means the right hand side dl by dt also has to be 0, which in turn means L is a constant, or angular momentum is conserved. So in the case of an isolated system, we have shown that the angular momentum is conserved. Now in the case of central force motion, the conservation of angular momentum follows directly from Newton's laws, as we have shown just now. But in the case of non-central forces, this is not very straightforward. You cannot predict the conservation of angular momentum just using the Newton's laws. For example, if you consider the force between charged particles which are moving with respect to each other, here the force is not central. So if you look at the angular momentum of the two charged particles, you find that it keeps changing and the angular momentum is never a constant. So you may be tempted to think that the conservation of angular momentum is violated in this case, but that's not the entire story, because here you have forgot to include one very important aspect, which is the field, the electromagnetic field due to these two charged particles. Because fields can have mechanical properties just like particles. They can possess energy, they can have linear momentum, they can have angular momentum. Okay. So if you consider the angular momentum of only the two charged particles, clearly that is not conserved. But if you take into account the angular momentum of the field as well, and you will find that the total angular momentum, which is the angular momentum of the particle plus the field, that will be conserved. So conservation of angular momentum is a universal principle which is true in any isolated system. So in summary, when the external force acting on a system is 0, its linear momentum is conserved. When the external torque acting on a system is 0, its angular momentum is conserved. And we are already familiar with the manifestations of conservation of angular momentum. When we discussed the case of planetary motion, we have seen that since gravitational force is a central force, the angular momentum of the planets by default are conserved. That's why they will rotate with much higher speed when they come closer to the sun. Okay. We can also talk about other examples. For example, if you look at an ice dancer. Okay. So when the dancer rotates with both the arms extended, you will find that she is rotating with a particular velocity. But when she keeps her hands close to her body, you will find that the rotational speed increases dramatically. Now, this is a direct consequence of the conservation of angular momentum. We know that angular momentum L is a product of moment of inertia I and angular velocity omega. Okay. And moment of inertia depends on the distribution of mass, right? So when the dancer extends her arms, here distribution is larger, so moment of inertia is also large. Okay. On the other hand, when she keeps her hands close to her body, the distribution decreases. Consequently, the moment of inertia also decreases. But the rotation happens in a central force field, the gravitational field. So the angular momentum has to be a constant. So when moment of inertia I decreases, to keep angular momentum constant, angular velocity omega increases. That's how the rotational speed increases when the dancer keeps her arms close to her body. So this is a direct consequence of conservation of angular momentum. You can find several such examples related to your daily experience. So with that, we come to the end of module 3, which also marks the end of our syllabus, SJPHY1 D01 Mechanics 1. Thanks for being with me throughout this course. Goodbye.